Hello everyone, this is Dr. Zach again. Today we're going to find the derivative of inverse functions. So let's get started. So today's lesson preview gave you an opportunity to review finding inverse functions. Now, remember, these are functions. So question B, when you were to find the inverse of G, you just exchanged your domain and range values in each one of these points. However, question C, the H inverse of X does not exist because the original H of X is not a function. And if H of X is not a function, then the inverse cannot exist. So as we begin thinking about the derivative of inverse functions, we want to pay special attention to the domain and the range of these functions. We will always define the domain of f inverse of x to be the range of f of x. And a function has an inverse if and only if it is one-to-one and is strictly monotonic. Strictly monotonic means that the function is increasing or decreasing on its entire domain. And therefore, if your function can pass both the horizontal and the vertical line test, then the inverse will exist. Now, it is possible for a function to exist and not have an inverse. However, if it does have an inverse function, that function is unique. There's only one solution. I also want to point out the graph of f contains AB if and only if the inverse function contains the point BA. For our first example, we're looking for y prime of the square root of 3. And what we do know is that y equals the inverse tangent of x. So what we'll do is rewrite the problem as x equals the tangent of y. And if x equals the tangent of y, we can use implicit differentiation to find the derivative. The derivative of x with respect to x is 1, and that will equal your secant squared y dy dx. Now, specifically, we were looking for y prime of the square root of 3, so let's now solve for dy dx. dy dx is equal to the cosine squared of y. Now, remember, I don't really want y as the value in the cosine. So we're going to let x equal the square root of 3. And we know that y equals the tan inverse of square root of 3 when y is equal to pi over 3. So the cosine squared of pi over 3 is going to be equal to our dy dx. And therefore, we will have 1/2 squared equals dy dx when x equals square root of 3. All right, so now let's look at example 2. This one says arc sine. So arc sine is a slightly different version of the sine inverse, and we'll get into that detail in just a minute. So we know that y equals the arc sine of x. I don't know its derivative, but if I take the sine of y, that would equal the sine of the arc sine of x, and then we know that x equals the sine of y. So this problem is very similar to the last. When we find the derivative, we have 1 equals the cosine of y dy dx, or dy dx is equal to 1 over the cosine, wait a minute, of y. But I don't want y. Remember what y was equal to. This is 1 over the cosine of the arc sine of x. All right, so we should be thinking about what is the difference between an arc sine and an inverse sine, or even the tan inverse. Their domains are actually different. So let's go back and look at the inverse tangent again. If I draw my tangent function, the tangent function has repeating patterns every period of pi. Now, if I were to rewrite the problem so that it's an tan inverse function, the inverse doesn't actually exist. It has an infinite number of answers. So what we do is put some restrictions on this function. We're going to consider the tangent function to have the boundaries from negative pi over 2 to pi over 2. Now, with those boundaries, what that does is it changes the domain for your inverse function to become -1, negative infinity to infinity, and the range is going from negative pi over 2 to pi over 2. If we put this restriction on the range, then what will happen is we are allowed to find the inverse derivatives. As we think about this arc sine, let's consider the sine function again. The sine function starts at 0, starts repeating, the period is 2 pi. What we're going to do for the arc sine is something similar. We want the domain of the arc sine to go from -1 to 1, and in order to get all the values between -1 and 1, we can go from negative pi over 2 to pi over 2. So really, we're just going to consider this one bit of the entire sine function whenever we talk about an arc sine. So the domain of the arc sine is going from -1 to 1, and the range of your arc sine is going from negative pi over 2 to pi over 2. In that case, once we make those restrictions, the inverse of the function will exist. So just as with all derivatives, continuity and differentiability make a difference. We need f to be a function whose domain is on the interval I. If f has an inverse function, then the following statements have to be true. F is continuous on its domain. Then f inverse is continuous on its domain. If f is increasing on the domain, then f inverse is increasing on its domain. Same thing goes on with the decreasing. If f is differentiable on the interval containing c, then the derivative of c is not 0, and the inverse is differentiable at f of c. So these ideas are going to be connected to find whether or not the inverse function has a derivative. All right, so the derivative g prime of x is equal to 1 over f prime of g of x, where g is the inverse of f. And we are actually going to show that in the next slide. All right, so our goal is to figure out what is the derivative of f inverse of x. So we're given that y equals f inverse of x. We're going to solve for x. So that tells us that f of y is equal to x. Now when we find the derivative, once again, we use our implicit differentiation, a very handy tool. F prime at y times dy dx is equal to 1. So dy dx is equal to 1 over f prime of y. But we don't want to have f prime of y. The good news is we know this is 1 over f prime, and then we're going to replace the y with f inverse of x. So there you have your derivative. The derivative of the inverse function is equal to 1 over f prime f inverse of x. Geometrically, let's take a look at what's happening here. If we look at the slope of the secant line, so that would be delta y over delta x, and we were to draw it in, that's going to be your change in y over change in x. But if we look at our inverse function at BA, there we go, these slopes are actually reciprocals of one another. So the derivative is going to be 1 over f prime of a, or the y value. So if these slopes are reciprocals, that's going to give us lots of different ways to figure out the derivative of our inverse functions. For example 3, we're told that f at 4 is equal to 6, f prime at 4 is equal to 2/3, f prime at 6 is equal to 3 over 5, and we're looking for the derivative of the inverse function of 6. So my thought is I like to write x, I like to write f of x, just to help me keep my numbers straight. So I have 4 and 6. So if these are 4 and 6, then that means that the x and f inverse of x are going to be 4 and the x value is 6. Just to help keep myself organized. So if I'm looking for the derivative at 6, and I know that f prime at 4 is 2/3, then the derivative of the inverse function at 6 is going to be equal to 1 over f prime of the y value, which is 4, and that will equal 1 over 2/3, or 3/2. So let's take a look at example 4. For example 4, we're looking for the inverse derivative at 1. So what we know is that 1 must equal f of x. And therefore 1 must equal x cubed over 32 plus x minus 5. Solving this equation, we're going to have a nice little cubic, and you may use your calculator to solve, or you might even be able to do it with your mind. You come up with x is equal to 4. So next we need the derivative of x, f of x. So f prime of x is going to be 3 over 32 x squared plus 1. We're going to take f prime of x and substitute in our 4. So f prime of 4 is going to be 5 over 2. From here, we know that the inverse derivative at 1 must be equal to 1 over f prime at 4, and therefore it's 1 over 5/2, or 2/5. So we're going to use the idea that the derivatives of our inverse functions and our functions are reciprocals to solve many of these problems. So now why don't you give questions 1 and 2 a try? Turn the video off. Afterwards, check your answers. Let's look at example 5. We're looking for g prime of 3, where g prime is going to be equal to the derivative of our f inverse of x. So since we're looking for g prime of 3, that allows 3 to be equal to f of x. And when 3 is equal to f of x, that would mean that x is equal to 4. So f prime at 4, according to our table of values, is going to be equal to 2. So then g prime of 3, which is equal to the reciprocal, which is 1 over 2. Now, when I'm looking for g prime at 4, that means that we're looking for the x value to be 2. So 2 equals your f of x. The derivative at 2, f prime at 2, is going to be equal to 3. So then g prime at 4 is the reciprocal, which becomes 1 over 3. Now let's look at example 6. We're asked to find h prime at 6, where h prime of x is the inverse of f. So begin by figuring out where f of x is equal to 6. We see that f of x is equal to 6 when x is equal to 3. Next, we want to figure out what is f prime at 3. So go to your other graph, which is the derivative of x. Notice what's happening. The derivative at 3, 1, 2, 3, is equal to 6. So we know that f prime at 3 equals 6, and h prime at 6 must equal the reciprocal, which is 1 over 6. All right, on the next page, you have some practice problems to work out. Spend some time on these questions and then check your answers at the end.